In this video for VCE Algorithmics students, we cover graph traversal algorithms, i.e. a systematic approach to visiting every node in a graph. This could be to find a particular node, such as an end state in a graph, could be to crawl and index a website, it could be for garbage collection, it could be for finding all connected components within a graph. It could be for colouring in a graph so that no two adjacent nodes share the same colour. It could be for topological sorting, working out which things need to occur before which other things. Also, social networks, degrees of friendships, and all kinds of other things. We are going to consider breadth first search and depth first search. In breadth first search, we traverse all neighbours in layers, working outwards from the source node, whereas with depth first search, we follow each path as far as we can go, going back once we get to the end. Starting with breadth first search, we visit all neighbours of a particular node, let's call them level 1. Then we visit all the neighbours of level 1 neighbours, which we could call level 2. Then we keep going in the same manner until we run out of neighbours. We use a queue to decide which vertices to visit. We look at the node at the top of the queue, then we remove it from the queue and add all of its neighbours to the queue. We normally mark neighbours visited when we in-queue them so that we don't add them multiple times before they have been dequeued. Let's examine this with a graph. I started by adding A to the queue. I dequeue A and then I add all of its neighbours in order. B is now at the top of the queue, so I dequeue B, add all of B's neighbours, which are C and E. Next I dequeue F, add F's neighbours, which there aren't any. Next I dequeue M, add M's neighbours, which are H and G. Next I dequeue C, add C's neighbours, which are just D. Next I dequeue E, add E's neighbours, of which there are none, so I dequeue G, add G's neighbours, which are J and K. I dequeue H, add H's neighbours, which are none, dequeue D, which means I add N, and then I dequeue J, K, and N, none of which have any neighbours. Now we're in-queuing in order, which means in alphabetical order, which means we're going to be dequeuing in alphabetical order because a queue is first in, first out. So in summary, we add a node to the queue, mark it as seen, we dequeue the top node, call that the current node, and then we get all unseen neighbours, mark them as seen, and add them to the queue. We're going to do this again with a graph which contains cycles, which means we need to mark nodes as visited, otherwise we get stuck into an infinite loop. So we start by adding A to the queue. A has been visited, then we add B, F, and J. Now the first one in the queue is B, so we dequeue B. There are no neighbours of B that haven't been visited, so next we look at F. F has unvisited neighbour N. Next we dequeue J. J has unvisited neighbours C, D, and G. Next we dequeue N. N has unvisited neighbour E. Next we dequeue C. C has unvisited neighbour H. Next we dequeue D. D has unvisited neighbour M. Next we dequeue G. G has no unvisited neighbours, so we dequeue E. E has no unvisited neighbours. We dequeue H. H has unvisited neighbour K. We dequeue M. M has no unvisited neighbours. And finally we dequeue K, which of course has no unvisited neighbours. The queue is empty and so we stop. One application of BFS that comes up a lot is finding the shortest path in an unweighted graph. Here we have a game called Rush Hour where you have to slide the vehicles around to try and get the red car out. Very good fun. And we can generate all possible states from any particular state and then work out how many moves it takes until we get to our target state. Moving on to depth first search, this time we are working with a stack. We start by adding A into the stack. We add its neighbours B, F, and P. We've added them in alphabetical order, but the last one that we are going to pop is the top of the stack, which in this diagram is actually the bottom, just because of the way it presents on the screen. So we pop P, and we add all of P's neighbours, which are C and E. So then we pop E. We add E's neighbours, which is just D. We pop D's neighbor, which is N. We pop N, which has no neighbors. I think I said that wrong earlier. Never mind. The next one we're going to pop is C. C has no neighbors, so the next one we're going to pop is F. F has neighbors G and H. Next we're going to pop H. H has no neighbors, so next we will pop G. G has neighbors J and K added to the stack, so we're going to pop K. Then we're going to pop J, and finally, if we go back up, we can see that B was the last one to be visited. Again, we'll do this on a graph that contains cycles so we can see the importance of marking nodes visited once they're added to the stack. And just make that absolutely clear, whether it's BFS, DFS, queues or stacks, we mark them visited as soon as we add them to the queue or the stack so that we don't add them twice. So we start by adding A, then we dequeue A, add its neighbors B, F and J. We pop J, add its neighbors C, D and G. We pop G, add its neighbors, which are none, so we pop D, add D's neighbors, which are N and M. Pop N, add its neighbor E. Pop E, it doesn't have any unvisited neighbors, so pop M. M has unvisited neighbor K. We pop K, unvisited neighbor H, so we pop H. H has no unvisited neighbors. We go back on the stack, we can see the next one is C. C has no unvisited neighbors, and likewise for F and B. And if you now look at the order that we've visited the nodes in, you can see how we've taken that sort of go as deep as possible approach until we have to turn back to the last point where we had a choice to go somewhere else. A classic use of depth-first search is maze solving. We want to find a complete path quickly rather than investigating all possible paths. We can also use depth-first search to detect cycles. To do this, we need to change the way we mark nodes. We need to have unvisited, visiting for nodes which have been added to the stack, or visited. And a cycle exists if we ever find a neighbor that is being visited, i.e. already in the stack. We must use 3 colors if using directed graphs. If we were using undirected graphs, we could use just 2 colors, but say ignore the parent. So let's see how this works. This is the same graph we had before, but I've taken some edges out, so it takes a bit longer to find a cycle. So we pop A, add its neighbors, and see once we've visited A, we've changed it to a different color. Next we pop J, add its neighbors C and G, pop G, nothing happens. Pop C, add D and H. Pop H, add K. Pop K, add M. And when we visit M, one of its neighbors is still in the stack. So at this point, we have detected a cycle, and if that was all we wanted to do, we could stop the algorithm. It's worth mentioning time complexity. For both BFS and DFS, they are big O of V plus E, which means the time taken to traverse a graph increases linearly with the sum of the vertices and the edges. If that means nothing to you for now, don't worry, but it doesn't hurt to think about them now, as you will see them when you read around the subject. So, in summary, breadth first search works by traversing all neighbors in layers working outwards. It uses a queue. We can use it for the shortest unweighted path and for a check of bipartiteness, which I'll cover in my next video. A depth-first search, we traverse each path as far as possible, going back once you reach the end. Instead of a queue, DFS uses a stack. We can use it for maze solving and connected components, and both algorithms are big O of V plus E. In my next video, we might look at the code in a bit more detail, and we will look at some applications of BFS and DFS, including graph coloring, connected components, and checks for bipartite. Leave a comment if you have any questions or anything you'd like to see covered in more detail.